My name is Allouche, professional engineer, associate professor of civil engineering at Louisiana Tech University, and the technical director of the Trenchless Technology Center. I obtained my undergraduate and master's degree in the areas of civil engineering at Queen's University. It's up north in Ontario, Canada. Then I earned my PhD at the University of Alberta in geoconstruction. I served as a faculty member at the University of Western Ontario and then joined Louisiana Tech in 2003. One resource that really helped us to advance our research and technology development very, very quickly towards a commercial product is our high-performance computer capabilities. Okay. That enables us to conduct simulation, really shaving a lot of time and a lot of cost of our development effort, taking a concept to a working product within a few short years. High-performance computer coupled with high-end numerical modeling enable us to model the propagation pattern of ultra-high frequency antennas. Our area of research deals with the development of electromagnetic sensors. Those sensors work on frequency which is very high, between 3 and 10 gigahertz, that 10 to 3 billion cycles per second, with some of our pulse length are virtually in the order of the amount of time that it takes light to travel 3 millimeters. Try to do those kind of analysis experimentally, it's very costly and time consuming. The availability of the high-performance computer and appropriate modeling software enable us to carry those analyses numerically, quickly and effectively, and obtain an accurate result. But for that, you do need a very, very large computer, such as the Loyola system, since many of our models have 3, 4, 10 million elements in them. Our work focuses on the development of new technology for buried infrastructure, in particularly the development of advanced electromagnetic and acoustic sensory systems. Two examples of projects that we're currently underway include the development of an electromagnetic sensor that actually travel into the pipe and secure the safety of the public that drive the road above us. Many people may or may not realize that under a street we have 1 million miles of sewer pipe. That represents investment of hundreds of billions, if not trillions of dollars, in probably one of the most basic elements of a civil society. We have to maintain and ensure the integrity of those pipes to protect our groundwater table, to protect our environment. Okay? Because we want to make sure that the raw sewer get down to where it can be treated and discharged safely. However, many of those pipes are in the ground for 70, 80, some pipes as much as 150 years. And over that time, they have deteriorated. When a pipe deteriorates, under some condition, we do have the bedding environment, the soil around it flowing into the pipe. However, this is exactly the same soil that supports the road, the street or the roadway above it. Okay? Unfortunately, when sufficient erosion takes place, when you drive down the street, you may find out that that pavement just collapsed beneath you. Our sensor is capable of traveling down that pipe and detecting very accurately the location, the size of that void before public safety is compromised, and thus we are able to repair it and fix it before any harm is done. Another project that we are doing is related to safety of excavation. We mentioned the 1 million mile of sewer pipe, but if you add to it a water line, telecommunication, natural gas line, there are well over 11 million miles of utilities buried underground. If you think it is, crowded above ground, try to live underground. However, our society required the expansion of our buried utility infrastructure to accommodate growth of population growth, as well as to accommodate new technologies such as fiber optics. For that, we have to excavate, we have to dig into a street, into our cities, and lay down additional utilities. However, when we excavating for new utilities, we do not wish to damage the existing utilities. Our technology can be mounted, is a very, very small sensor that can be mounted at the cutting edge of excavation equipment and actually provide the operator with real-time warning as to the presence of a utility along the trench. So as to alarm him that, stop, there is a utility there that you do not want to strike, both protecting the utility, of course, protecting the safety of the operator and the general public. The current state of the art, the current technology is really relying on video cameras that are sent down the pipe and to try to take images to detect different defects or different compromised buried utilities. At the moment, there is no technology out there that actually can give you information about any kind of imperfection, defect, or void outside of the pipe. So in a sense, the technology is unique and it's the only of its kind in the marketplace. We have, in terms of economic impact, when we talked about the fact that maybe there is no technology that can do what we do, but there are many cameras there, there are 17,000 units out there. Virtually every city in the US have one or more of those transporters, those mobile cameras that can go into pipe and tell you what's in there. Our system is basically able to be mounted and be made compatible with each one of those 17,000 systems, greatly amplifying the information that a municipality can get from every dollar that they put into inspection of the buried infrastructure. The economic benefit for the end user, with the municipality and the general public, is the fact that you're able to get much more information from the same amount of dollars spent. Okay. In a sense, it costs you a certain amount of dollars, typically $1 per foot, to put one of those cameras into the sewer. However, you get information only on what's happening inside the sewer itself, any kind of damage, crack, and other defect within the inner wall of the pipe. Now, for virtually the same amount of investment, you get information about any kind of decay within the pipe wall, as well as any kind of defect, soil, void, or other hazard which exists outside of your pipe. So you double or triple the data that you receive for the same amount of money.
Talk a little bit about how your innovation and how it relates to a particular application that spurred some type of a commercial activity or an industry partnership. What has that done and how has that helped to facilitate taking it into the marketplace?
That particular technology, our FutureScan or PScan sensory system, was awarded a $3.2 million federal grant. That grant was awarded to Loyola University together with our two industrial partners. One of them is a lead industry market, probably the leader in our industry for inspection of buried pipe, and the other is another very well-established technology company. And it resulted in the creation of a spin-off company, Beyond Vision, located here in Ruston, Louisiana, with the objective of developing that technology and bringing it to market. Really, the concept of that invention that probably can contribute to the public safety of every citizen in a country really came from the idea came from the aftermath of Hurricane Katrina. our biggest city, New Orleans, is sitting on very fine clay. I mean, the clay in New Orleans is a river sill that actually been transported down there by the Mississippi River. It's highly transported, and therefore soil void beneath road is not an uncommon event in New Orleans. And that was actually the occurrence or the frequency of those kind of soil void grew dramatically in the aftermath of Katrina due to the damage that caused to the city. And when I was watching the news and learning about those soil void, my thought was, what can we do to help? What we can do to protect those people. There is no reason why a mother that's taking their child to school need to fall down a 20 feet, into a 20 feet diameter sinkhole, or a child that go back home, be any kind of a risk that the sidewalk beneath him collapse. What can we do in order to try to ensure the safety, to detect those kind of hazards? And really that was what prompted the concept of the future scan technology. Absolutely. We have 11 million miles of pipe beneath us. And we don't think about it, but it's an entire world down there that we need to serve us. We need to serve our need for heat, for communication, for water, for sewer. However, those facilities, if they are not in good structural condition, they can actually pose a public risk to ourselves and our children. And we believe that technology such as FutureScan will provide this added public safety. Give us that assurance and peace of mind that yes, it is safe to drive down a street. The interest in that particular technology stems from the fact that it is the only technology out there that economically can give you information about any kind of defect in the wall of the pipe or outside the pipe. That technology can be deployed when the transporter or that robot is traveling down the pipe at 30 foot per minute. So we can collect a very high resolution data at a very high speed, representing a relatively low cost increment over and above collecting a regular data of video images. So the combination of additional information coupled together with a very low cost to provide a valuable data that assists with public safety. Research is just like any other business. We have to listen to our customer. The Trenchant Technology Center have 18 forums around the country annually, which are attended by 1,000 municipal engineers. We listen to them, we listen to what keeps them awake at night. Knowing what the needs are out there is the first thing that a researcher needs to do. You have to solve a problem, a real problem. The second important thing to have a successful product is you have to reach the right people. Our center have a 50-member strong industry advisory board, which include the city of New York, Los Angeles, Atlanta, Houston, Denver, Dallas, and many others, as well as the largest company of the industry. When we have a concept and idea solution, such as our FutureScan, we're able to communicate that immediately to the vice president or the head engineers of those companies or cities, getting right to the top, delivering a clear message to the right people. Finally, the third component for a successful technology is the confidence of the client in you. The company or city or any other entity will be investing many millions of dollars in that technology, bringing that to market, taking it from the lab into a commercial form. They have to know that you have the intellectual capability, you have that high caliber faculty member. They have to know that you have the numerical capability, the high performance computer to do it, the software, and that you have to have the experimental capability. You need to have the laboratory, the full-time technician. You need to have the ability to deliver, to actually transform it from a prototype on a laboratory desk to something that is rigid enough to work in the field day in, day out, in the end of a crew, a construction crew or any other crew. Okay? A product that can be manufactured not only utilizing very expensive laboratory equipment, but actually can function using cost-effective electronic and computer board. A product that's going to be resilient enough not to require repair every other week. They have to know that you have ability to deliver that. And I believe that in our future scan project, we were able to demonstrate all of those three parameters, both to our industry partner as well as to the National Institute of Science and Technology that provided us with that $3.2 million grant. And be able to demonstrate those three components is what brought that success. The state of Louisiana, through its public university, provides academic and inventor with the academic freedom to go seek and develop, pursue our idea, pursue our invention, pursue our dream, and try to develop them to a point where we can find investor to actually go ahead and try to commercialize it. It provides us with the computer system, the computational capability such as the Loyola system, with the high-performance computer, with the laboratory space that we need to foster our idea, to foster our dream, and make it into a reality. The most important thing that the state of Louisiana and the legislature can do to assist researchers like myself and my colleague is to provide reassurance and commitment to the fostering, development, and advancement of research and development within public universities in Louisiana. This kind of reassurance is something that our industrial partners are looking for when they are investing the dollar in us. They are looking for, because they not only are investing in terms of long-term research project which can span over multiple years, multiple millions of dollars, they also are counting on hiring a graduate student that are developing those technology to be there and to operate those technology when they reach market. And they want to make sure that those laboratories, that those graduate classes, that those advanced programs are there 3, 5, 10 years down the road, that they'll be able to get the return that they expected for the investment that they are making today. The art of every university research program are a graduate student. Okay? They're not only the people, the individual in the lab, the individual that spend days and night working and developing and advancing a research program. They also are the individual that when graduate will spread the word, will take those new ideas and new concepts and embed it in the industry, embed it in everyday practice. They are also a faculty member of the future. Okay. They are individuals that become to be community leaders. They will be engineers or they move to other discipline, but they will be the community leader. They will be the individual that will start all those startup companies that will prompt and develop new technologies, new industries. Graduate students, educated young individuals are the future of our society. We are working very closely with our industrial partner. We have about 20 research projects with at least 14 or 15 different companies. Our graduate student and our undergraduate research assistant are in a continuous contact, not only with the management, but also with the technical member and technical staff of those companies. They are visiting their facilities, they're becoming familiar with the needs, familiar with their operation. They contribute to their operation, and themselves they gain much understanding as to what they learn in the classroom, how it's applied in the real world. So in a sense, we're getting the benefit of both worlds. the educational world and the research world contributing to the industrial world, new idea, new concept, and more importantly, new mind, fresh mind. As well as our educational world, we're learning from the industrial world as to how things are done in the real world and how to better prepare a graduate for that world. It's important to understand that today in the industrial world evolves rapidly. Okay? The needs that were 3 or 5 years ago are different than the need of the industry today. In academia, we have to accustom ourselves to that rapid change and adjust our teaching method, teaching material to prepare a graduate for that global, fastly evolving economy. I believe that perhaps the largest environmental threat to the US right now is coastal erosion. This problem is concentrating in Louisiana, particularly in southwestern Louisiana, where we're losing a meter an hour. It is an existence threat to the state of Louisiana, and it is an environmental threat to the Union. We are working right now on a very exciting research project, which we believe will be able to manufacture up to 30 million tons of artificial rock from purely waste material that can be effectively used to stabilize the coastal region of Louisiana and help to restore the wetland. Every year, the Corps of Engineers mine over 20 million tons of silt from the Mississippi River and its tributes. At the same time, every year, coal-fired power generating plant produce well over 8 million tons of fly ash in the process of producing electrical energy. We have developed a unique formulation that enables us to combine about 80% silt together with 20% of that chemically bounded, chemically stabilized ash to create a soft rock. We can create that material at a cost of about $15 per cubic yard, which is a fraction of the cost of concrete. You can make that material, which is chemically stabilized, we can make that material completely out of waste product, thus not affecting the housing market by increasing the cost of material and ingredient that are used for the construction of homes and businesses. Therefore, we can restore our coastal line. We can protect and restore Louisiana coastal line while creating hundreds, if not thousands, of jobs in Louisiana with no adverse economic effect on our economy. I feel that as an engineer, the role of our profession is to care for public welfare. This is the destination, this is the role, this is what we assume on ourselves when we become to be a civil engineer. This is a role, this is a historical role. My family and I found a home here in northern Louisiana. We found a home here in Raston. We love our community. I love my university, and I want to see it prosper and succeed.